We grow up learning that movement requires effort. Pull a toy car by a string and it moves. Let it go and it stops immediately. Our everyday intuition is built in an environment saturated with mechanical friction and fluid drag. These invisible opposing forces bleed kinetic energy from moving objects, creating an illusion about how reality actually works. This environmental bias led the Greek philosopher Aristotle to conclude that an external force is an absolute requirement to keep a body in motion. To uncover the actual rules of mechanics, we have to strip away that intuition. We need to construct a theoretical world entirely free of friction. Galileo bypassed the messy reality of friction by using the clean geometry of inclined planes. He imagined a ball released from rest on one slope. It accelerates downward, then climbs the opposite side. In a perfectly smooth system, the ball will always seek to return to its exact initial release height, regardless of the second slope's steepness. If you decrease the angle of that second incline, the ball still reaches the same vertical height, but it has to travel a much longer horizontal distance to get there. Pushing this to its mathematical limit, if the second plane is perfectly horizontal, the slope is 0. To reach its original height, the ball must roll an infinite distance. Its journey never stops. The state of rest and the state of uniform linear motion are mechanically equivalent. An object moving with a constant velocity is doing exactly what an object at rest is doing, maintaining its baseline state. Isaac Newton built upon this geometric insight, codifying it into the first law of motion. The law states that if the net external force acting on a body is precisely 0, its acceleration is 0. The object will resist any change to its current state, a property known as inertia. A spacecraft in interstellar space, with thrusters completely shut down, experiences 0 net external force. It glides forward with constant velocity forever. Here on Earth, a book sitting stationary on a desk is also unaccelerated. It is not free from physical forces. Rather, the downward pull of gravity and the upward normal force from the table perfectly cancel each other out. 0 net force describes a state of perfect dynamic equilibrium, where an object's future trajectory mirrors its past. If a net 0 force simply maintains the status quo, we need to define the exact mechanical function of a non-zero external force. The answer requires a new variable, momentum, denoted by p. Momentum is the product of an object's mass and its velocity. It represents the total currency of motion an object holds. A heavily loaded truck crawling along a road and a tiny bullet fired from a rifle can require the exact same opposing effort to stop. They possess vastly different masses and speeds, but their total momentum can be identical. Newton's second law defines force as the rate of change of this momentum over time. Force equals the derivative of momentum with respect to time, dp over dt. For an object with a constant mass, this simplifies to the familiar equation, mass times acceleration. By defining force as a derivative, Newton's definition tethered the concept of physical effort to the flow of time. This time dependency is highly practical when we look at impulse. Impulse is the measurable product of an applied force and the time duration over which it acts, resulting in a finite change in momentum. Think of a cricketer catching a ball traveling at 90 meters per second.
Bringing that mass to a complete halt requires a massive, fixed change in momentum. To execute this safely, a seasoned player pulls their hands backward at the exact moment of physical contact. This graph illustrates why. Both curves represent the exact same total change in momentum, but by linearly extending the time interval of the catch, delta t, the peak force required to stop the ball drops exponentially. Surviving high-energy impacts is rarely about fighting momentum head-on. It is an exercise in stretching time to diffuse the force. There is a strict constraint built into the second law. Force dictates acceleration exclusively in the here and now. Imagine accelerating forward in a speeding train, holding a stone out the window. The instant you let it go, the physical connection to the train's engine is severed. Air resistance aside, the stone falls in a parabolic arc. The stone retains the horizontal velocity it had the moment it was dropped. However, its horizontal acceleration drops to exactly 0. It carries no memory of the train's forward thrust.
A moving particle's trajectory is blind to its history. Its acceleration is dictated strictly by the local force vectors acting on it at that exact microsecond. Since isolated bodies simply maintain their momentum, we have to ask, where do external forces actually come from? Newton's third law answers this. Forces never occur singly in nature. They are strictly mutual, symmetrical interactions between pairs of bodies. Look at the exact moment of impact between two unanchored masses. A common misunderstanding assumes that because these forces are equal and opposite, they should cancel each other out to zero. They do not. The forces do not cancel because they are applied to completely different bodies. The force on A alters A, and the force on B alters B. Calling them action and reaction creates a false sequence in our language. There is no cause and effect, only a single, simultaneous event experienced from two different perspectives. If we stop analyzing individual particles and instead draw a boundary around the entire interacting system, a mathematical consequence emerges. Multiplying these opposite forces by their contact time, delta t, yields impulse. Substituting momentum proves the momentum gained by object A equals the momentum lost by object B. Rearranging terms, we group initial states on one side and final states on the other. The total final momentum of the system equals the total initial momentum. We have just derived the universal law of conservation of momentum directly from local first principles. Conservation holds true across multidimensional space, extending from simple linear paths into complex spatial planes. Consider a billiard ball striking a rigid boundary at a specific angle, then reflecting perfectly off the surface. This diagram traces the vector components of that impact. The momentum component parallel to the wall remains identical. The impact only alters the component perpendicular to the boundary, perfectly inverting it through the normal force. Extrapolating this to a closed system of any size, every single internal interaction occurs as a perfect mirrored pair. The total momentum of a closed system cannot be altered by forces acting within it. Local particles will constantly collide, push, and accelerate, but through the symmetry of Newton's laws, the total momentum of the universe remains constant.